Welcome to Get Your FRQ On. This question is from the Calculus AB exam, 2007 version B. It's question 3, and it is a calculator active question. The stem for this question gives us a function for determining the wind chill given various parameters. And in part A of the question, we are asked to find the derivative of the wind chill function, W prime, evaluated at 20. 20 here represents the velocity of the wind. And after we find it, we are also asked to explain what this value means using the correct units. So first, we'll differentiate our wind chill function, W of V, for the value V equals 20. When we take the derivative at 20, we get negative 22.1 times 0.16 times 20 to the negative 0.84 power. This is just a straightforward application of the power rule. There's nothing really fancy here. The only thing really going on here is that there's some decimals here. You have to do a little bit of arithmetic in order to get the correct exponent when you're done. But other than that, it's not too bad. Since this is a calculator active question, we use our calculator to determine a specific value for W prime of 20, although the way that free response questions are scored, if you have a numeric response that doesn't require any further algebra to simplify, if it's just numbers and operations, the standard is they will accept that answer if it is numerically correct. So even though this is a calculator active question, it's not entirely necessary to use your calculator to come up with a specific value for W prime of 20. We could leave it as the expression above, but it might be a little bit unwieldy later if we need that value. So for the time being, we'll just use our calculator to get a number for this, and then we can use that number later if we need to. So when we plug it into our calculator, we determine that W prime of 20 is approximately negative 0.286. Now, given the question, since we have to explain what this means with correct units, what this result means is that the wind chill is decreasing at a rate of 0.286 degrees Fahrenheit per mile per hour. And one of the things we have to watch out for here is when we are asked to evaluate a derivative and explain what it means with units, to keep track of our negative signs. Since the derivative here is negative, the negative sign indicates that the value is decreasing. So we have a couple of options here. If we say that it's decreasing, we've already accounted for the negative sign, and then when we give the rate at which it's decreasing, we would give the positive value of that derivative. If we say it's increasing, that's okay, but we would have to include the negative sign in our rate. So be careful how you accommodate and give negative signs and describe values as either increasing or decreasing. Certain combinations can be correct and other combinations can be incorrect. For part B, we are asked to find the average rate of change of W on the interval from 5 to 60, and then using the mean value theorem, finding the value of C at which W prime of C is equal to that average rate of change. So the first thing we're going to do is we are going to find the average rate of change of W on the interval from 5 to 60. So we'll take W of 60 minus W of 5 over 60 minus 5. That's just the formula for average rate of change. 60 minus 5 is 55. Since this is a calculator active question, we can use our calculator to actually determine values for W of 60 and W of 5. Again, it's not absolutely necessary to use your calculator here. You could use very lengthy expressions that indicate what W of 60 would be and what W of 5 would be, but I'm not sure you want to do all that writing. It is probably just easier and faster to plug this into your calculator and get a number, and it's allowed on this question, so you might as well take advantage of it. So using our calculator, we can determine that W of 60 is approximately 13.050. W of 5 is approximately 27.010. That difference divided by 55 is approximately negative 0.254 when rounding. Keep in mind, when you round decimals on free response questions, the expectation is that you round it or truncate it to 3 decimal places. So make sure you don't overestimate and over round and things like that. You can lose a point for insufficiently precise answers. So be careful when you have to do that. All right, so to find the value of C at which W prime takes this value, we're going to use our calculator. We're going to graph the function W prime of X. Technically, it's W prime of V, but on a calculator, you're going to type in X. So we plug that into our Y equals editor as one of the functions. We want to know when that is going to equal negative 0.254. So what we can do is enter a second function in a second Y variable, just graph the horizontal line negative 0.254, and then use our calculator to determine where those two graphs intersect. There are other ways to do it. We could add negative or add 0.254 to W prime of X and find an X-intercept or something like that. But it's just as easy to set them as different functions and find out where they intersect. So if we do that, we find that W prime takes the value negative 0.254 when X is approximately 23.011. Again, you could do this algebraically. You don't need a calculator to do this, but it's kind of a lengthy process, solving an equation using logarithms and things like that. You don't need a calculator to do this, but because it is a calculator active question, you are supposed to have a calculator with you when you take this part of the exam. You might as well take advantage of it. Just set it up graphically, use the capabilities of the calculator to find that value for you. In part C of the question, we are asked to find the rate of change at t equals 3, given some other criteria as well. And what ends up happening is, in order to find dw dt at t equals 3, remember dw, well actually the function w is defined in terms of v, and so dw dt is sort of a hidden application of the chain rule. So really what we're after here is if we want dw dt, we need to find dw dv times dv dt. So dw dt when t is equal to 3 is going to be dw dv times dv dt at t equals 3. So we have w prime at 35. The 35 is part of the given for this question. And we're also given that dv dt at t equals 3 is 5. So we have w prime of 35 times 5. And when we calculate what that is using our calculator, w prime of 35 is negative 0.178. Multiply that by 5, and we get negative 0.892 degrees Fahrenheit per hour. And that is the solution to 2007B, question 3.